In section 6 of chapter 17, we're back to talking about free energy. This time we're going to look at free energy and chemical reactions. There are a few ways that we can calculate the standard free energy change. That's delta G with the little degree symbol here. Remember, standard means 25 degrees Celsius and 1 atmosphere for the temperature and pressure. We can use this equation that we talked about in section 4. We can also use this equation here. It's very similar to an equation that we have used for both entropy and enthalpy. To calculate the standard free energy change for a reaction, we will take the sum of the standard free energy of formation for the products minus the sum of the standard free energy of formation for the reactants. You can find these values in Appendix 4. The standard free energy of formation is the change in free energy that accompanies the formation of 1 mole of that substance from its elements. Don't forget, when using this equation, that N represents the number of moles, which would correspond to your coefficients. In this video, I will not go through an example using the second equation because we have already done this for entropy and enthalpy. There's also a third option for calculating the standard free energy change, and that is using Hess's law. I'm not going to show an example in this video of that either, since we already did that with enthalpy changes. So what I will focus on is this first equation right here. Let's first think about an example where we just predict the signs of the standard enthalpy change, entropy change, and Gibbs free energy change. We're going to form a stable diatomic molecule spontaneously from its atoms. So that would maybe look something like this. I'm just going to use A for my atoms and A with a subscript of 2 for my molecule. Let's talk about the standard entropy change first. We have atoms that form a molecule, and so this is less disordered, and so our entropy change would be negative. Now let's think about our standard enthalpy change. We have bond forming only, and so that is exothermic, and that sign would also be negative. In section 4, we talked about if the enthalpy change was negative and the entropy change was negative, that delta G would be negative if the temperature was low. But here we also have an additional clue. We are told that this is a spontaneous process. So that means that our standard free energy change is also negative. Now let's consider this system at equilibrium at 25 degrees Celsius. That is the standard temperature that is required. We have our standard free energy change that's indicated here. It is negative, so this reaction is spontaneous. We would like to know what will happen to the ratio of the partial pressures of the phosphorus pentachloride to the partial pressure of the phosphorus trichloride if the temperature is raised. Let's think about the sign of our enthalpy change and entropy change first before we tackle that problem. If you remember in section 5, we said that when a reaction involves gas molecules, the change in entropy is dominated by the relative numbers of molecules of gas reactants and products. We can see here that we go from 2 moles of gas reactants to 1 mole of gas product. This would mean that the entropy change is negative. When we subtract a negative number, that means that we are adding. So that must mean that the enthalpy change is negative in order to get a negative answer for the free energy change. When the enthalpy change is negative, this means that the reaction is exothermic. If we increase the temperature, we are adding heat. And so according to Le Chatelier's principle, the reaction will try to absorb that heat and the reaction will shift left to make more reactant and less product. The partial pressure of the phosphorus pentachloride decreases. The partial pressure of the phosphorus trichloride increases. Therefore, the ratio decreases. Now let's be a little bit more quantitative with our equation. We are going to calculate the standard enthalpy change, standard entropy change, and standard free energy change for this reaction that's given using the following data. Let's calculate the standard enthalpy change first. We'll take the sum of the heats of formation of the products and subtract the sum of the heats of formation of the reactants, shown here. The answer is negative 198 kilojoules, which I will now put in for my standard enthalpy change. Now let's do a similar calculation for the standard entropy change. For an answer we get negative 187 joules per Kelvin. We would expect this to be negative because we've gone from 3 moles of gas on the reactant side to 2 moles of gas on the product side. Before I can substitute this in for my standard entropy change, I need the units to be in kilojoules to match the kilojoules for the standard enthalpy change. I divide by 1,000 and get 0.187 kilojoules per Kelvin. Now all I need is my temperature in Kelvin. My temperature in Kelvin is 298, and when I go through and solve that, I get negative 142 kilojoules. The kelvins have canceled. And finally, just a side note about these standard entropies. You'll notice when you look in Appendix 4 that elements and compounds have positive values. Gases will tend to have higher entropy values than liquids or solids. And the more complex the molecule is, the higher the entropy tends to be.